Okay, here's our third and final example with the pulleys. Now, this situation looks a lot similar to example 2, except we added one factor. And that is that our table now, we're no longer assuming that there is no friction. We're assuming that is a rough surface, and that there is some coefficient of kinetic friction. So the object will be moving. We're assuming that when we start looking at this, it's already in motion. So we're not worrying about the static friction coefficient. We are also assuming, like the other two, that our string has no mass. It is a rigid object, which means it's not stretching. We're assuming that our pulley, there is no friction in the bearings, and that our pulley itself has no mass. So, same three questions as the other two. Choose each block. As a system, draw a force and motion diagram. So let's get started. System A. Again, accelerating to the right, block B accelerating down. So we can assign our directions on our sketch. We will be assigning them on our motion and force diagrams as well. So it's accelerating. Show that with our motion diagram. Delta V going the right direction. It's times 0. And go. Force diagram again. It's going to look essentially the same as the previous one, except we're adding one more thing here. Again, our top and side arrow, top and bottom arrows should be the same. I'm going to put a component here. We've seen this before. It's in the Y direction. This is table on our box A. This is the force Earth on box A. Have a horizontal force again. This is force string on A. And then we have one more factor, and that's we have some kinetic friction going on here. So it's not going to be enough to stop it, so it'll be smaller magnitude, and it resists the motion of our object. So if our object is moving towards the right, it's going to be pointing towards the left, our friction. So that is, this is the reason why we chose our components. This is the force in the x direction of our table on our object, which is box A. And I'm going to label this box A. Okay. So that's first system A. Now we move to system B, box B. Motion diagram speeding up, accelerating in the positive direction according to our sketch. Times 0, negative, positive, delta V, pointing down. Our force diagram, again, it's going to look similar to last time. So here's B, minus, plus, force Earth on B, force string on B. Remember, same as last time, This force here should be the exact same length as this force here. Okay? They are interacting, they're connected to each other, they're accelerating at the exact same rate. So that's part A. Part B. What is the acceleration of each block? Again, this should be accelerating at the same rate. So we go to our mathematical model and word statements. Acceleration is equal to the sum of the forces over the mass. Again, this equation, our word statement, sum of forces, comes directly from our force diagram. We're focusing in the horizontal direction for this block because that's the direction in which it's accelerating. So acceleration is equal to the force string on block A plus the force of table in the x direction on box A divided by the mass, box A. We don't know the acceleration yet. We do not know the force string. On box A yet. Okay, so now this force here. Okay. This is, we're dealing with friction now, right? So this friction, table on A in the x direction. Let's give to our mu times our normal force. Okay? Normal force is the force that is perpendicular to the surface. And what is that? That is force table in the y direction on our box A. And we can solve for that. We know it's the same magnitude as force Earth on A. So N, the normal, is equal to the mass of our object times g, which is our acceleration for Earth. All right, so that's how we break that up. That's how we split that up. So we have our numbers now. Friction coefficient, 0.2. We have the mass, which is 10 kilograms. And we have g, 9.8 meters per second squared. Divided by the mass of our object, which we know to be 10 kilograms. Okay, and this 9.8 is negative, again, because it's pointing, the normal force is pointing in the upwards direction, but also our friction is pointing in the negative direction. So we would be assigning this as our negative force. Multiply both sides by 10 kilograms. 10 kilograms times our acceleration is equal to the force string on box A. Multiply these all out, and we get a negative 19.6 kilograms times meters per second squared. Move this over to the other side, add both sides by 19.6, and we get 10 kilograms A, and that's equal to 10 kilograms times A plus 19.6 kilogram times meters per second squared. That's equal to the force spring on box A. Or I'm not spring, force string on box A. So we'll leave that where it is and go back up to our system B. Acceleration is equal to sum of the forces. It's now in the vertical direction, or the y direction. Acceleration is equal to, again, these forces come right from our force diagram. Force string on B plus force earth on B divided by the mass of B. Do not know acceleration. We do not know the force string on B. Acceleration is 9.8 meters per second squared multiplied by our mass, which is 25 kilograms. Again, we're assigning this to be negative. It's going in the negative direction. And it's over the mass of box B, which is 25 kilograms. Okay, multiply both sides by 25 kilograms. You have 25 kilograms times our acceleration is equal to the negative force string on B plus, and this is 245 kilograms times meters per second squared. Move this over to this side, add both sides by a positive, subtract both sides by a negative. You get force string on B. It's equal to a negative 25 kilograms times our acceleration plus 245 kilograms times meters per second squared. Okay, before, two systems, two equations, two unknowns. Solve for our acceleration. 10 kilograms times the acceleration plus 19.6 meters 19.6 kilograms times meters per second squared is equal to negative 25 kilograms times acceleration plus 245 kilograms times meters per second squared. Add both sides by positive 25 kilograms times acceleration. Subtract both sides by 19.6 kilograms per meter squared. We end up with 35 kilograms times acceleration is equal to 225.4 kilograms times meters per second squared. Divide both sides by 35 kilograms. We have our acceleration. And that's equal to 6.44 meters per second squared. Now, if you took a look at the previous example, we saw that when there was no friction, the acceleration was actually equal to 7.0 meters per second squared. So now that we have an extra external force exerting on our block A into the negative direction, it makes sense, it should make sense, that our acceleration here is less than the acceleration of our previous example where there was no friction. If you end up with a larger number, that's one way to check that we added some friction, it's going in the opposite direction, it's exerting a force resisting the motion of our object, and so yeah, our acceleration should be less. So the force is less, acceleration is less. So move on to our final part. Find the tension, find the force that the string exerts on block A and the force string exerts on block B. So mathematical model, sum of the forces divided by the mass. Acceleration is equal to the force string on A plus force in the x direction table on A. This is divided by the mass of A. Acceleration we solved for before, 6.44 meters per second squared is equal to the force string on A plus negative 9.8 meters per second squared. Remember, this is the force x in the x component, horizontal component, table on box A, 10 kilograms times our kinetic friction coefficient of 0.2. So I'll divide by our mass of 10 kilograms. Multiply both sides by 10. We get 64.44 kilogram times meters per second squared. And that is equal to force string on A and minus 19.6 kilograms times meters per second squared. Add both sides by 19.6, and we end up with our force string on A is equal to 84.0 kilograms times meters per second squared, or newtons. And we'll do it again for the other. This is good practice. Acceleration is equal to the sum of the forces over the mass. Acceleration is equal to the force string on B plus force earth on B divided by the mass of B. Acceleration 6.44 meters per second squared is equal to the force string on B. That is plus 9.8 meters per second squared times 25 kilograms. So I'll divide by the mass, 25 kilograms. Multiply both sides by 25 kilograms. We end up with 161 kilograms times meters per second squared. And that is equal to our force string on box B, plus 9.8 times 25 is 245 kilograms times meters per second squared. Subtract 245 from both sides. And we end up with the force of string on B is equal to 84, so negative 84 newtons or kilograms times meters per second squared. And so if we look back at our previous example, we saw that, again, they were the same magnitude, opposite direction, which we should agree with, because it matches with our sketch, matches with our force diagram, matches with our motion diagram. But the force here is now a larger number. It's a larger magnitude. What did we do? What was the change from this to the other one? Well, we added some friction here. Okay, we added a rough surface, which wanted to pull, resisted the motion of our object. Essentially made it feel like it was more massive because it's resisting this motion. It's just another force, another interaction. It's not that it was more massive, it just, this block doesn't know, it has to pull harder. But the block itself isn't pulling, it's the earth is pulling this block. The string, this block is pulling this string, and the string is then pulling A. So there's this two-body problem where, because we're adding this extra coefficient of friction, the forces in here, the interaction between the string and our objects actually becomes greater. Okay, so I hope this helps with pulleys and two-body problems. These are just 3 examples, and good luck on the rest.